a Regents professor. You can understand it as a chair professor, okay? And he is also the vice dean of the School of Engineering from Arizona State University. He has been doing the water treatment and wastewater treatment for over 20. So he has done lots of excellent work in this area, in a lot of very cool things like emerging contaminants, nanotechnology, innovative treatment processes, and also wastewater reuse. So it's our greatest honor today to have Professor Paul Westerhoff to give us the presentation. Thank you so much. Please start.
Great. Thanks, Jin. Thanks, Doug. And thanks, Dong, for figuring out the logistics there. So Jin asked me to talk for about 40 minutes. Is that still correct?
Yeah.
Great. And so welcome. So I'm Paul. I'm from Arizona. As you can see the photograph here, the sun is coming up in the morning in Arizona. And so the fun thing about this program you put together, Doug, is there's things going on in different parts of the world. It's also pretty dry here, so we don't have a lot of water. So water is very important to us. Water does exist in Arizona, though. We have mountains, and the Grand Canyon is probably the most famous landmark of Arizona. Arizona is located in the southwestern United States. I'm at Arizona State University that has 102,000 students. Lots of students, and the easy way to remember Arizona State University is if you look in a mirror, it's USA backwards. Welcome to Arizona. So here's an outline of what I'm going to talk about today. I'm going to talk a little bit about where we get water from and why they're located in different places. And then I'll go into the goals of water treatment and some general layouts of these systems. Because of time, I wasn't able to include the hydraulic design approaches, but if there's any questions about that, we can talk about it. So this is, no matter where you are in the world, pretty much where cities grew up. They grew up along rivers. Sometimes they're located downstream of mountains. Sometimes they're quite far away from water sources. If you follow the little blue dot here, water comes into a water treatment plant through a city and downstream. So there's a saying in the US, not everyone can live upstream. Many cities are located on rivers downstream of other cities. And the water then carries pathogens. These are microbial constituents, inorganic chemicals, and trace organic chemicals that we use in society. Even though we purify the water through wastewater treatment plants, they'll still go into a river and downstream. And so de facto reuse is one way to kind of track how much of this water of wastewater origin comes downstream. And I'll talk about that just a little bit later, because as we have larger populations and the same amount of water, more of our wastewater is getting reused over and over again, whether it's intentionally or unintentionally. So of course there's impacts on rivers and ecosystems for things like fish, but also we have to remember that the ultimate goal of drinking water treatment is to provide safe and clean water, both out of the tap as well as for industrial or bottled water uses. In the United States, in the blue here, the bottom right, is the number of surface water treatment plants that serve communities over 10,000 people. You see most of them are located on the eastern part of the United States. Here's New York City. Out here in Arizona, we have a smaller number of them, and then on the West Coast. In between, there's less population, but there's probably about 10 times more dots would be on here for groundwater treatment systems. So generally about 10 to 1 more systems use groundwater, but in the United States, over 60% of the population is served by surface water. And then you can see the corresponding location of wastewater treatment plants. And this is a map, again, of the United States and looking at whether people are located downstream of wastewater treatment plants. And what you see here is about half of the United States drinks surface water that has wastewater located upstream. So this is a real change over the last 40, 50 years as the populations have grown, that we have new types of chemicals. These are chemicals from industry, chemicals that we use every day, and they're not just the weathering of minerals. And this doesn't only occur in the United States. This is the Yangtze River in China. So here's Shanghai, I think, down here. But as you go downstream, there's a greater contribution of wastewater into the river. And even when you consider the river gets larger, this de facto reuse, or the percent water of wastewater origin, increases as you go downstream. And there can be in-stream processes that help purify the water. But the point here is that watersheds are very important to think of as your first barrier of understanding of water treatment. In the United States, people think about multiple barriers of protection, but in the end, you do need water, and it does come from a variety of sources. Not all their sources are always natural rainfall sources. This is what can happen when runoff from agricultural sources happens. This is one of the Great Lakes, and the green that I'm showing here are algae blooms. So there are water treatment plants located in this area here and also around Cleveland and near Detroit, and that these are seriously impacted by algae. So algae will affect the performance of a water treatment plant, but in this case, it can also have cyanotoxins. Now, these are pretty easy to remove, but again, it's an influence of every water source is going to be different. Consequently, every drinking water system tends to be a little bit different. In the United States, about a third of the population relies upon groundwater, and many of those systems will be publicly owned systems, but about 43 million people in the United States have private wells with little or no treatment at all. I want to spend just a few minutes talking about what it is in the water that we're trying to treat. These are, by one indicator, what we're not doing the greatest job at removing. So total coliform is a type of bacteria. Fecal coliform would be of wastewater or human origin. And these are the number of violations over this time period. So you can see that bacterial contamination, even in well-operated water systems, is a major source of violations in the United States. The second one, a large group, is related to nitrate. Nitrate is a chemical from agricultural origin, both in surface water and in groundwater. Arsenic, lead and copper. This is not lead and copper that's in the source water, but actually comes from the plumbing and pipes in the distribution system. So one goal of water treatment is to stabilize water to prevent byproducts. In this case, these are corrosion byproducts of pipes. Another category of byproducts are called disinfection byproducts. You can see this large blue bar of these number of violations, and I'll talk a little bit more about them later. But these are the types of things which we're not doing the greatest job at, whereas other things are not on here. So we don't have big issues of organic contamination of our water with chemicals like PCBs or other specific chemicals. And this just shows that trajectory of these violations, and these are change over time. In this case, you would see that between 2000 and 2005, the number of violations went up by a factor of 3 or 4. This isn't because water treatment got worse. It's because the regulations got more stringent. As the regulations got more stringent, the number of violations apparently went up, but then as water treatment plants changed the technology, you can see that they went down between 2005 and 2015. So in the United States, water treatment plants are heavily regulated by federal and state agencies that set specific goals and targets for removing chemicals. Ultimately, one of the challenges of water treatment is to protect human health. And so there's a number of ways to think about what that means. And this is just, again, in the end, to remember that we're making water for people. And these are risk maps of bladder cancer across the United States. And bladder cancer, one of the leading causes, is associated with some of the byproducts in drinking water. And if you want to look more specifically, I'm not sure how to get rid of the red lines there. I'm just going to try one thing here for a moment. I'm not sure how they got on there. Try that again. Well, we'll have to live with them for a second. But this is another way of looking at risk factors. And in this case, you see that the central part of the United States with this dark blue actually has the highest risk of total number of violations. And this type of thing allows counties, which are the small squares here, to understand and investigate how to improve water locally. So we can look at national trends, but oftentimes water is very specific. And if it happens in your city or in your town, it's a very big concern. For example, a few years ago in Flint, Michigan, the drinking water treatment plant changed from one river source to another river source and didn't account for the corrosion that could happen in the pipes, and it released a lot of lead into the drinking water. This is in this town of Flint, Michigan. And as a consequence, lead is very serious. The lead was not in the river water, it came from the plumbing and was released as a function of corrosivity of the drinking water. And lead in children causes serious irreversible neurological problems. So there's a whole number of other chemicals that we'll find as a function not of what we do to our water, what we put in, but because of geology. Here's a map of nitrate, for example. Same types of maps exist for geology of arsenic, which is naturally occurring. And these types of information are also occur globally. Here's an arsenic map based upon predictions of relative risk based upon geology. So as you think and here's fluoride as well. So as you think about what water communities will do, some of it's going to be centralized and some of it will be personal decisions. In the end, people might want to put additional purification systems on their tap at home. They might use systems from the office or at airports to drink better tasting water. Generally, municipal water systems provide very safe water, and these types of devices are generally used more for aesthetics. So hopefully that concludes the first part of the talk, giving a little bit of an understanding that before we think about how to have a water treatment plant and what to put in it, we need to understand what is in the water that we're trying to treat. So then thinking about the goals of water treatment, you can see a list here. We're trying to remove chemicals that might be in the water. We're going to remove particles. Not that all particles are bad, but you don't want to drink a glass of red water. Many of the particles will be of biological origin, but only a very small number will be potentially infectious to cause intestinal acute health responses like diarrhea or vomiting. Whereas chemical exposure may be over a very long time and cause things like cancer. So very different endpoints for different types of chemicals. Water treatment plants also try to prevent those corrosion and disinfection byproducts I mentioned, as well as make water aesthetically pleasing in terms of taste, odor, and color. And water treatment plants are seriously challenged to do this very inexpensively. In the United States, about $1 to $3 per 1,000 gallons of water. I think I did the conversion right, but maybe about 5 won per cubic meter of water. So at a municipal scale, you can treat large volumes of water very inexpensively, but that really affects the type of technologies you choose. In the United States and in most countries, individual chemicals are regulated, as well as approaches for monitoring and regulating pathogens. And there's a big difference. Chemicals are measured as an individual chemical on very sophisticated instrumentation, whereas microbial pathogens, oftentimes we use what are called surrogates. So it's very difficult to measure one virus in water in real time. So therefore we use indicators like turbidity. Turbidity is caused by the number of particles in water. So if you do a very good job at removing particles, you're probably doing a very good job at removing things like bacteria, oocysts, things like Giardia or Cryptosporidium, as well as viruses. And in the United States, you get what are called credits. You get some credit for physical removal of particles, and then you get and require some credit for chemical inactivation. So you need to add things like oxidants that are disinfectants. And you're given different scales and based upon the type of water you're treating, whether your objective is to remove 99%, 99.9%, or 99.99% of the pathogens. Even though you don't measure them, it's a type of a credit system. Now, if this is a wastewater reclamation facility, they're going to try to achieve what are called 12 logs. That would be 99.9999999% removal of the pathogens. But again, you don't actually have to measure the viruses that are there. So very different approaches for these different constituents. Now I want to spend 2 minutes talking about two different types of byproducts. One type of byproduct are called disinfection byproducts. So we add oxidants to water to kill pathogens, to kill viruses. The consequence or side product of that is that the oxidants will react with organic matter in water. It's kind of like if you went to a river and you saw tea. Tea comes from putting tea leaves into water and organic molecules leaching out of the tea. The same thing's happening when leaves and soils interact with our water system that cause color. And things that cause color can react with the oxidants and form things like trihalomethanes, this chloroform down here. So it's a serious concern because things like these disinfection byproducts can be quite carcinogenic. So on one hand, we're adding oxidants to water to disinfect it, but we have to balance that against the risk of forming long-term carcinogens and exposure to carcinogens. Now, a lot of people have focused a lot of time on developing models of these things, and it's useful to understand things that control things like chloroform formation. And it's the total organic carbon content of the water. That's what I was describing, that tea-colored material. The dose of your oxidant, in this case chlorine. The presence of things like bromide, because chlorine can oxidize bromide that then gets incorporated into these byproducts. Warmer water temperatures form these higher amounts and faster. pH affects these, and the longer amount of time. So many water treatment plants, between the time the water leaves the treatment plant and gets to your house, is somewhere on the very short side of 3 or 4 hours. And in the United States, that can go up to about 21 days. So the longer the time the water sits in the pipes being exposed to things like chlorine, the higher the concentration these byproducts may be. Now, the other very important type of byproduct, as I mentioned in Flint, Michigan, related to lead, is corrosion byproducts. This is a cross-section of a pipe, and the blue material here is it's a copper pipe, but copper pipes will form malachite, a blue scale on the inside. So sometimes people will have blue water and it's a scale flaking off. One of the things about many new buildings these days is that when you first put in copper pipe, they will corrode and you do get exposed to copper. And then down here, you can see that these iron pipes also will rust over time and have iron. And as you change the chemistry of the water, maybe seasonally or because it changes in water treatment performance, you can release these corrosion byproducts and get into your drinking water. So you can control those by managing the pH and corrosivity of the water. So with that as a background, there's various pollutant removal mechanisms that are used at water treatment plants. And these are just some of them that I have time to kind of go through one graph at a time. And I'll spend just one page on each of these processes, each intended to remove different types of chemicals or microbial pollutants in water. The first is something like gas addition. There's a variety of gases used in water treatment. In this example, maybe we're adding ozone gas to water. We usually bubble it through the water, but the ozone gas has to migrate from inside the bubble across the gas liquid interface and become dissolved in the water. And only then can it react and disinfect the microbes. So we have to manage and understand how to add gases to water. And the principal mechanism here is something called Henry's constant, if you want to learn more about it. Now, in some cases, we want to remove dissolved gases, kind of have this go the opposite way. Examples there might be hydrogen sulfide. Hydrogen sulfide causes many groundwaters to smell like rotten eggs. It's not a health issue, but it's a purely aesthetic issue. And so by bubbling air through water, you can take that dissolved gas and strip it out of the water so the water is treated and would not smell anymore. But so there's a number of gases that we can add and remove from water. The second one is oxidation. And the main reason we want to add an oxidant to water is to disinfect the water. So in the bottom right-hand side here is an image of some cell that could infect you. And in the red box, I show that chlorine destroys DNA and protein activities. This is how these disinfectants work. They prevent replication of organisms, and in some cases, they'll kill the organisms. But if the organisms can't replicate, you're not going to get sick when you ingest water and this enters your gut. So many of the disinfectants I've talked about, chlorine, chlorine dioxide, ozone, are chemical oxidants. We also use UV disinfection. In this case, this is the absorption spectrum, this red line, for DNA. So if we apply light at 254 nanometers, it's really close to the peak absorbance of the DNA molecule. So it'll absorb the UV light and it'll actually break the DNA bond. And so UV is an example of a non-chemical disinfectant. So we also add ozone and chlorine as oxidants. They'll oxidize iron and manganese in water. They'll also, ozone's very effective at removing those algal toxins I talked about as well. So there's many reasons why we might want to add an oxidant. Frequently, it's for disinfection. Then the next process is called precipitation. So particles that have been in a lake water for many months are not going to settle out in a few hours in a water treatment plant unless you change their chemistry in some way or change the number of particles in solution. So one very typical thing that we do is we add a chemical to water. Here it's aluminum sulfate or alum. Sometimes people will add an iron. And when you exceed the solubility product, you form aluminum hydroxide, which is a solid. And this will precipitate out this new particle, this gray particle. Other particles in water, kind of the red and blue dot, or the red dots here, will become enmeshed in that as this aluminum hydroxide starts growing, or might stick to the surface. It also turns out that aluminum hydroxide is pretty effective at absorbing that tea-colored material, that total organic carbon. So by adding a chemical to water, we make particles, in this case, the aluminum hydroxide particle, that helps us remove both other particles that we don't want, like viruses and bacteria, but also absorb organic pollutants to them. So that would be the first step, is to make these particles. The second step is to figure out how to grow the particles large enough so we can get them later to settle out. This is a process called aggregation and flocculation. So the first step is to make chemically destabilized particles. Most particles in water, rivers, lakes are negatively charged. So by adding aluminum, which is a cation or positively charged, it neutralizes that charge. We make new particles, and then we create some mixing. This mixing is called flocculation. This moves the water around and allows particles to collide together. When they collide together, they'll start to stick together and they'll grow. Larger particles are going to be easier to remove through sedimentation processes. So that's what I'm trying to show in these little cartoons, is that this process of flocculation makes larger particles. Now, particles will enter a sedimentation tank. They may stay in there for 2 to 3 hours. And the idea is to have particles settle out of water. Now, a particle in water, as I'm showing the blue here, in order for it to settle, it has to balance a number of different forces. So the first is gravity is going to be acting on the particle. This is this force of gravity. But as anything starts moving down, there's some drag in the water. So that'll slow down the particle. And then we also know that buoyancy is very important. So if I put a rock in water compared to a balloon in water, right, they have very different buoyancies. And so buoyancy is going to be a force acting against gravity. So most of the time we're trying to settle particles out, and we can calculate something called a settling velocity. That's a function of the particle density and the density of the liquid, the diameter of the particle, and a gravitational force, and mu on the bottom is a viscosity of water, which is temperature dependent. So most of the time we try to settle particles out. Some particles are rather buoyant, like algal particles. And there, instead of sedimentation, we actually can design processes called flotation that brings the particles to the top. So if they're at the top, we can then skim them off. If they're at the bottom, we can collect them. And that way we remove these particles from the water, and we'll have to manage them, usually by going to things like landfills. So after we settle water and try to remove the bulk of the particles, then we'll go into a filtration process. I'll show some pictures in a little bit, but sand filtration is about about a meter deep. So the objective here is not a strainer. We're not removing particles because they're larger than the pores in the sand. Instead, we want particles to migrate into the sand bed and really collide and stick onto the surface. And that's what I'm showing in this upper right-hand graph. This gray circle is our sand collector, and these are these small particles we're trying to remove. So in general, you can see that the collector is many times larger than these particles. Most particles we try to remove in water treatment in a filter are in this order of 1 to 10 microns in size. And so we can calculate the efficiency of a filter to remove these as a function of length or depth of the filter based upon the particle, the size of our sand, the porosity of water, a transport process called eta, and something called alpha, which is a stickiness factor. That is how sticky these particles are. So for each of these mechanisms, there are driving equations which engineers understand on how to design water treatment processes. I'd say over the last decade or two, membranes have been used more than sand filtration. They do cost more. It's about 5 times more expensive to design a membrane filtration plant than a sand filtration plant. But membranes, there's 2 types, those with pores in it or those with holes in it. And then those that are more like jello or just a solid polymer matrix that water and ions diffuse through. So first, in terms of the pores, there are microfiltration and ultrafiltration that will reject particles larger than the pores. But what I'm trying to show in this graph up here is that the radius of the particle to the radius of the pore. So if your particle is equal to the size of the pore or greater, it'll be 100% removed or rejected. However, we can still get about 50% rejection of particles that have a ratio about 0.5. And that really has to do with the electrostatics around the pore and the way that water moves, usually cross-sectional or cross-flow across the membrane, whereas water moves down through the membrane. So you can remove particles smaller than individual pore sizes. The other type is reverse osmosis. In the United States, this is widely used for desalinating seawater, as well as desalinating wastewater. So it's very efficient at removing salts and a wide variety of organic chemicals. The next process is adsorption. There's many different types. The 2 most common types are ion exchange, and the other is activated carbon. In general, ion exchange is used to remove inorganic ions in water, things like nitrate and calcium, whereas powder or granular activated carbon are used to remove nonpolar organic chemicals. And so these occur through different processes. The ion exchange will have, say, chloride on the surface. Nitrate will come along, bump off the chloride, and stick on instead. To remove calcium, calcium will come onto near the solid sorbent and kick off sodium. And you can regenerate these systems over and over. Activated carbon is a highly porous kind of charcoal-like material. And your dissolved molecules have to diffuse into these pores of these material before they can absorb onto the surface. There's different ways to quantify the amount of adsorption. The most typical way is using an isotherm or something called absorption capacity, where it's the mass of the chemical that's present on some amount of sorbent. And this would be how we design the system. And there's different ways to relate this K as a capacity, and 1/n has to do with the strength or affinity of an individual chemical for an individual surface. Now, in addition to understanding how much can absorb, mass transport kinetics become very important. So if I put something like this activated carbon in water, it may take 2 or 3 weeks in order to come into equilibrium. That is, the mass transport or movement of the chemical within these pores can be very slow. So understanding how to design that, such in a system where maybe your water's only in contact for 10 minutes, is a real engineering challenge. So hopefully that describes some of the mechanisms that are used. Now I want to show you some pictures of different types of unit processes that we employ those mechanisms within. And here's a general layout. You'll see some pictures in a minute where we try to remove large material. This can be trees and seaweed types of materials, coagulation and flocculation where I try to make particles and then grow them, sedimentation where I try to remove the large particles. And we can't forget that they go somewhere. They leave the water, but we have to manage them. Then water after sedimentation goes into sand filters and then things like disinfection. So here's a water treatment plant to give you some scale of what these look like. I'll show a photograph in a minute, but again, a little bit different process. And here showing how and where we add different chemicals to water. This is our chlorine is anywhere it's green here is a disinfectant, for example. And in some cases, we actually add fluoride. In about 30 or 40% of the US drinking water treatment plants, we add a small amount of fluoride for dental protection. So you can see it's a pretty complicated system. And here's what that looks like. This size that you see the cars back here, this is enough, this is a water treatment plant to supply water to about 150,000 people. So they become pretty efficient systems. These aren't always the prettiest types of things, but this is where the water comes out of a river or lake through a pipeline, usually through screens to trap this large material, keep fish out of your water treatment plant. This is then without the water in the tanks. You can see the concrete tanks here. There's a variety of different ways we can mix chemicals into pipelines, and then we also physically mix the water to allow particles to start to collide with each other. So these would be flocculation basins. And again, here, this is under construction. It's not a great photograph, but you see that these are lined up in series, in series going this way. So water flows through different treatment trains. So it's not one big box. This is about 6 different treatment trains. That way, throughout the year, you can expand or reduce the amount of capacity of water going through the treatment plant without changing the hydraulics dramatically. This is an example of sedimentation tanks. On the upper left-hand corner here, behind here, would be kind of rectangular tanks. Sometimes they're also circular tanks. I like this picture again because you can see what it looks like with water in it versus one that's empty. And in this case, water will come in the middle and then move to the outside. So the reason that these are circular is as water moves to the outside, it's actually slowing down. And so particles are settling in here along the way, colliding with the walls. At the bottom will be a collection system for that sludge. And it's a little hard to see, but around the outside is what's called a V-notch weir. So water will flow over the V-notch weir. So you can control the spread of water across that whole system. Here's a system that looks very similar, but it's actually quite different. In the middle is they're adding lime to the water, and they actually recirculate the water in the middle at a very high pH, and this allows them to remove calcium from water at the same time. So similar types of things from the outside can have very different things going on inside these unit processes. So after sedimentation is filtration. This gives you some idea of a scale. Here's a worker down inside of a filter that they're putting. It's about 2 meters, a meter deep of the sand that they bring in these bags. And then you'll operate these filters for about 1 to 7 days. And then you have to clean them because you had particles stick in them. So you have to you turn off the water, you fluidize the bed, and then the sand media will rise up to about this level here. The dirty water will come over into these troughs and then out. So normal operation, the water essentially going through the floor that this guy is standing on. So these are an example of filters. And you can see how it's laid out here. Water will come in, move through the filters, and then there'll be a gravel support and under drain to take out the clean water. And then to backwash it, you would turn off the outlet. You would take this high pressure water, fluidize the sand, clean it, and the dirty water would come out the top. Here's an example, much more compact. These are a microfiltration membranes. Inside of these modules are a number of, these are hollow fiber. They look like straws inside of there. And these are cleaned about every 20 minutes compared to the sand filters, which may be on the order of days. On the left here, these are reverse osmosis membranes. You can start to see the size and scale of these membrane systems. And on the upper right are ceramic membranes. So many the membranes I've been talking to up to this point are largely polymers, but you can also make them out of ceramic material. They're much more durable, but they cost more money. Then after you remove those particles, you have different types of disinfection. There's a lot of computational fluid dynamics used to design how water and chlorine react together. And so here's an example in the bottom left-hand corner of these serpentine walls to have water move through these chambers. So you get very good hydraulics in as small a space as possible. In this case, you can generate chlorine on site, or you may have tanks of chlorine that are used. And on the bottom right here shows different types of UV reactors that people are using these days. And these UV reactors, there's a schematic on the right, an image on the left. You can also put chemicals in before them, like hydrogen peroxide, and that forms a chemical called a hydroxyl radical, which is a very powerful oxidant to remove trace organic materials in water, things like pharmaceuticals that may not have been removed by the other processes. And again, sometimes water treatment people forget that you need to handle the solids that come out of these. So you need to squeeze the water out of them, and then you generally load them up into trucks. The bottom left-hand corner here is something called a belt filter press, where literally you're squeezing the water out and making a pretty solid cake, kind of like a very dense mud. So I then want to show just a few images of a typical groundwater treatment system. Here there's fewer processes is one of the keys. And you see an example in the bottom right-hand corner from Arizona here, where they have essentially a small house with a pump in it. They have some vessels, and I'll talk about these in a minute. And you can see the scale, but this is enough water for what about 10,000 people or so. So one of the things that is often in groundwater that you try to remove is iron and manganese. So coming out of the pump, you might add air to the water and have one tank to remove iron. You might add a disinfectant or an oxidant and then remove the manganese. Here's some images of arsenic absorption systems. The upper right is essentially what looks like rust, but this is a porous iron material that goes into these vessels. On the left-hand side is a pretty small system, maybe for a community of 1,000 or 2,000 people. And the same material can be put into very large vessels in the bottom right to treat water for 10,000 people or so. So then sometimes you also have chemicals in water that are semi-volatile, things like trichloroethylene or TCE, which would be contamination, or MTBE, or other gasoline metabolites or products that leaked out of a gas station. And these are called stripping towers. So in here, water will come in the top, it'll trickle down over media, they'll be blowing air from the bottom, and that'll allow chemicals to be stripped out of the water. But here's a telephone pole, so you get the idea that these can be quite tall, and that as you're trying to strip out these chemicals from water. Sometimes you'll need to readjust pH in these systems. So you might want to or need to add carbon dioxide as an acid, right? It's a little bit easier sometimes to add carbon dioxide. And this is also important in terms of going back, as I mentioned, in terms of preventing corrosion. Stabilizing the water and having carbon dioxide in the water is one way to do that. So this is my last slide then, and think about some of the challenges of the future. Hopefully that gave you an overview of what people have been doing over the last few decades. but the population is growing and the flow in the rivers are not. So we need more water. So declining freshwater supplies will require more ocean desalination. But in the United States, the trend is really to have more desalination of wastewater. And the reason is shown on the right here. And these are costs I was able to find from China, but the cost of desalinating ocean water is going down. This is RMB per cubic meter of water. But you can see in comparison, the cost to desalinate and treat wastewater is about 4 or 5 times cheaper. Also, not everyone lives near an ocean. So desalinating ocean water is not always a feasible option. But you can see in comparison, the cost, and maybe I did get it wrong in my calculations, but the cost of cleaning and providing safe drinking water today is considerably cheaper if you're using river or lakes. And so this cost is a real major driver for why people are choosing different technologies. In the United States, some of the water quality trends are you're having more impaired water sources, more algae, more taste and odor, more toxins associated with those algae. You do have industrial spills occasionally and other accidents. There's mixtures of unknown chemicals in our water, and so regulating every chemical is one approach. An alternative approach is more proactive. You put in a technology like activated carbon, which will remove everything, not just a specific targeted chemical. There's also a lot of interest in the United States to use more data. This means more sensors, more monitoring and understanding how to use that information. And whether it's because of marketing and not the request of municipalities usually, but most people are using various types of what are called point of use devices. Those are things that you put on your tap at home to provide either that extra safety margin in your brain or make water taste better. And just to give you some idea, that is this graph at the bottom. This is the market and the projected growth of the point of use market. They use pretty high technology inside of these small devices. But you can see it's expected to more than double from about 13 or 14 billion dollars a year in the United States to nearly $30 billion a year by 2025. So this is definitely an important and growing part of the water sector because the public isn't trusting the safety and taste of the water they're receiving from the city. So Jim, hopefully that provided kind of the overview of drinking water treatment to start off the series, but I'd be happy to answer any questions.
Okay, thank you so much for the very informative and comprehensive introduction of the water treatment processes. So time for students. Any questions?
Hello, Professor. Thank you very much for waking up early for us for this compelling presentation. I have a question about emerging contamination. We are facing now more and more emerging contamination, right? Mostly maybe hormones. We're hearing a lot about it, and there is as well a rare earth element in the surface water. That there is some couple of cases reported found in drinking water. There is any adaptation in the system to kind of target these new and chemicals?
Yeah, so you know that I called them here trace organics, and only because one of my students made this little video. I'm going to play it again. If you follow the color of the dots, right, they start off nice and clean, and they change, and there's some, you know, even going through the river, they change again, and so you know many of these things that we find, these trace organics, are things that we consume every day, like artificial sweeteners, sucralose. So sucralose is not biodegraded in our gut, and that's why we don't get fat. And likewise, in a wastewater treatment plant, the bugs have a very difficult time biodegrading sucralose. So it's not removed at the wastewater treatment plant, and it's not removed well at a drinking water plant. But the concentrations are millions of times lower in tap water than in your soda. So some of these are, you know, people would argue that you have choices to take a certain medicine or to take a certain beverage, whereas drinking water, you don't have a choice. Okay, so then if it depends kind of where you go there. Other chemicals do have a real measurable effect. We published a paper recently on methadone. So methadone is used as a painkiller, and when it comes into contact with a type of disinfectant called chloramines, it forms another chemical, a byproduct, this disinfection byproduct called nitrosamines, which is very carcinogenic. So sometimes these chemicals or the byproducts of those chemicals do exert health effects. And so I think that was my final slide, that a lot of water treatment plants, and in Europe, the trend is to, especially in Switzerland, the trend is to put better treatment at a wastewater treatment plant to prevent them from getting into the rivers where fish and other things see them as well as people. So it's a decision on where you put some of that technology. But the technology that's well suited to remove those chemicals, those trace organic chemicals, are generally activated carbon, is quite efficient at removing, absorbing some of them. Then the UV hydrogen peroxide, or what are called advanced oxidation processes, are quite efficient. And then the other is reverse osmosis. But reverse osmosis is very energy intensive. It doesn't actually destroy, or it just separates and you form concentrated waste streams. And you form water that's actually not very healthy and is very corrosive. So in the United States, most people are moving towards either activated carbon or these advanced oxidation processes if the municipality has concern over those types of chemicals. Many of them are not yet regulated anywhere in the world. And in the United States, for a regulation to start and get enacted, it's about a 10 to 20 year process. And so most of by that time, individual drug manufacturers have already moved to another chemical. And so that's what I started off right in the beginning from, is that it's a multiple barrier system. You have to understand what's going on in your watershed. You can try to manage what goes on in your water treatment plant, and then also what goes on the tap. And so those barriers are where people are adding more and more layers of barriers and trying to use different sensors to understand, in this case, this example here is how much wastewater might be in your drinking water source, and maybe that will tell you about how to operate your water treatment plant. So hopefully that answers your question a little bit.
Oh, for sure, thank you very much.
Thank you, Professor Paul, for the very interesting course and the introduction on water treatment. My question is regarding the gases as well as the UV being used to treat the water. So after degrading the contaminants in water, what happens to them? So they may form additional products, right? Do municipalities or water treatment plants are concerned about the dangerous role of these intermediates that are formed after degrading these contaminants? What happens to them? Are they taking care of it? Or because just because, if, say for example, you have a textile dye in water, you use photocatalysis or UV degradation, color change, but definitely there are some byproducts which are of course formed. What happens to them?
Exactly. It's a trade-off, right? And so in different parts of the world, and as communities develop their water system, the first thing usually people try to do is to control and manage the acute health risk associated with diarrhea and vomiting. And that is the world's #1, killer of infants related to water is, microbial outbreaks. Okay, so that should be that first line. You need to do that well, right? And then the second is controlling these byproducts or these transformation products that are kind of illustrated on this diagram here. Most of these transformation byproducts, when you're concerned about them, they cause cancer. And so that means consuming water for decades. And so hopefully communities over that period can improve their treatment of these. And so it's an ongoing debate and very different philosophies in Europe versus the United States. The United States, we use very high levels of chlorine, largely to prevent bacteria and viruses getting into the distribution system in those pipes between the treatment plant and your house. And we try to manage things like chloroform, these byproducts, to as low a level as possible. And this trend that I showed in terms of these number of violations and how that changed over time, is in the direct response to that. So between 2000 and 2005, the stage 1 disinfection byproduct rule is this going, and they were trying to regulate the exact thing you said. So at one point you could average a concentration over an entire city. So this regulation changed. You had to meet it at a number of different locations. So, you know, the problem was someone that lived far away was seeing very high levels of these transformation products. So this regulation, even though, you know, this, what looks like a big increase, it was just a change in how and where we measure these transformation byproducts. They could see utilities understood how to manage the problem, and it's been coming down the number of violations. So you can see that this takes time. It takes decades in the United States for regulations and cities, because these are large capital investments and you don't want to do things quickly. When you do things quickly, you lead to other problems like corrosion problems like we had in Flint, Michigan and Washington, D.C. and other cities when they changed the way that they were treating the water. So people are very cautious. But you could argue that it might be okay to take 5 or 10 years to improve the water because these are carcinogens. Again, decades of exposure. So that's part of the argument. But yeah, these transformation products are a very big concern.
Thank you, Prof.
Can you hear me?
Yes, I can.
Oh, awesome. I'm just trying to figure out the microphone. Nice to meet you, Paul Westerhoff. I'm Verena from Trent University, and thank you so much for your talk. I have one question regarding more like chemicals, pesticides, and their registration, which I'm most interested in within my PhD research. So when new chemicals or pesticides are developed, do you know if there's anything implemented in their registration process that takes account for wastewater treatment? Because as you said, it might be like a longer process until new techniques for the removal are developed. So it would be ideal if even when pesticides get registered, there's something like there have to be tests provided that they can be removed from the water, because there are a lot of tests regarding ecotoxicology and human health. But I'm just wondering if there's specifically anything for drinking water.
Yeah, so not so much for drinking water. So at least in the United States, I can speak to this, is that when people come up with new chemicals to be used in society, so agricultural chemicals are a little bit different, but there is a test where you look at the biodegradation and absorption onto what are called biofloc at a wastewater treatment plant. And so the first thing you do is you do a projection. So for example, in the United States, there's something called the American Cleaning Institute, I think, ACI. And these are all the cleaning products that you use in your house. Things like soap products and everything, you know, fragrances in the soap, everything, not just the soap, right? And so the first thing they do is they'll do kind of a mass balance to figure out what the concentrations would be at the wastewater treatment plant, how much could be accounted for degradation in a river, and what could happen at a drinking water plant. So yes, when there are new chemicals used in society, they'll look at that. Now, in terms of chemicals that are used for agriculture, herbicides, pesticides, it's a little bit different. There, the focus tends to be more on terrestrial ecosystems and aquatic ecosystems, with a little bit less focus on drinking water systems. So there are guidelines and tests to screen these in the United States. But sometimes things happen. There can be spills and other things. So yeah, I mean, the water quality in the United States and Europe is very good, right? And the question is, just because you can measure something in the water, does that mean it's bad? You know, it might be thousands or a million times lower than any meaningful health risk. And so it's, with the number of new chemicals coming on the market that people want to every day, there are a variety of chemical and experimental screening protocols that are put through in the United States, before the EPA, the FDA, or US Department of Agriculture allows their widespread use.
That's good to hear. Thank you.
Well, great, Jin. I think we're at the top of the hour.
Yeah,
I'm happy
sure.
to stay on for a few minutes, but I want to thank everybody for calling in from across the world. It looks like a great program you have. Thanks for letting me be part of it.
Thank you so much, Paul. Thank you very much. Have a nice day.
You too.
Thank you.
Again, I'll say someone had a question here in the chat box. They're from Nanjing.
Oh.
Would you mind sharing the statistical data about contaminants with me? For example, the distribution data of nitrate and arsenic in the US. Yeah, so I didn't come up with the arsenic and nitrate maps, but feel free to contact, did I put my email on the final slide here? You can contact Jen or I, and I can provide that to you.
Okay.
Yeah, so there, my email address is on the slide there, Mr. Zhang, if you want to send that to me. And your second question is the fraction of arsenite in total arsenic, right? So very smart question. So arsenic can occur in two speciations, arsenate and arsenite. I don't have that data, but I can probably refer you to a US Geological Survey paper where they have that data. So feel free to send me an email, and I can provide you with that information, I hope. Thank you.
Okay, thank you so much, Paul. Thank you very much.
Bye-bye, everybody.
Bye. Okay, so I guess we are going to have the following two presentations in the next 2 weeks. So we are going to talk about, we will keep on the water treatment. So one is about disinfection byproducts, and another is about the issues happens in the water distribution systems. So I hope to see you all next week.